professor.
Lisa, I have news. Remember the art student I told you of?
Yes, Edith.
Yes, well, I have asked her to marry me, and she has accepted.
Oh, Dr. Han, congratulations.
Yes, well, I wanted you to be the first to know.
Oh, I'm very pleased for you. Very pleased.
Lisa Meitner was warm-hearted by nature. She had many friends, and she may have wanted to have a closer relationship with Otto, but it really does seem that physics was Lisa's first love, maybe even her passion.
The 1920s and 30s were the golden age of nuclear research. The largest known nucleus at the time was that of the uranium atom, containing 238 protons and neutrons. Meitner and Hahn were leading the race to see if even bigger nuclei could be created by adding more neutrons.
So, the atom, pretty familiar. Nucleus in the center, electrons orbiting around. The nucleus is our focus. The nucleus made up of protons and neutrons. Now, the largest nucleus that we know is that of the uranium atom. Its nucleus is a tightly packed structure of 238 protons and neutrons. The thrust of our work is to try to fire neutrons into this huge structure, and if we can get a neutron to stick in here, it will be a breakthrough.
Meitner may have been on the brink of a major discovery, but Germany in the 1930s was a dangerous place to be, even for a world-class scientist.
The U.S. endangers our institute.
When the Nazis came to power, one of the first things they did was to drive out Jewish academics from the universities. Einstein was very prominent, and for that reason, he was one of the first to go. He was hounded out of Germany in 1933. Lisa was not dismissed at that time. She was able to stay because she was Austrian. But in March 1938, Austria was annexed into Germany, and at that point, her situation became untenable.
What is it?
Frightening news.
What's happened?
Kurt Hess is going around saying that I should be got rid of.
I actually knew. I heard today I was going to speak to the treasurer of the institute before I told you. We'll speak to him tomorrow. Come on, let's get you home. It's late. We'll finish up.
The pressure on Meitner was unbearable. Hahn, who was known for his anti-Nazi views, did his best to protect her, at least initially.
I need to talk to you about Lisa.
Not now, I'm too busy.
We have to protect her.
How? What can we do? The situation is the way it is. Who knows what will happen next? She can't stay. It's just not tenable.
But she hasn't got a visa or even a valid passport. And she may soon be forbidden to leave Germany.
We can't harbor a Jew. If she stays, the regime will shut us all down.
Lisa. Fräulein demands that you leave.
You can't throw her out.
Fräulein says you should not come into the institute anymore.
Well, I have to write up then. Thorium irradiation tomorrow, so I have to come in.
You've given up.
When it became clear that Meitner would be dismissed and probably arrested, physicists all around Europe wrote letters inviting her to conferences, giving her an excuse to leave Germany. The Nazis refused to let her go. In July of 1938, a Dutch colleague traveled to Berlin and illegally took Lisa back with him on a train to Holland. The trip was so frightening that at one point she begged to go back. Despite the great danger, she got through.
She had lost everything: her home, her position, her books, her salary, her pension, even her native language. She had been cut off from her work just at the time when she was leading the field and was on the brink of a major scientific discovery.
No matter what privations she suffered, Lisa was still thinking of physics. Amazingly, she and Han were able to collaborate by letter.
I hope, my dear Otto, that after 30 years of work together and friendship in the Institute, that at least the possibility remains that you tell me as much as you can about what is happening back there.
Lisa was invited by an old student friend to spend Christmas on the west coast of Sweden. Her nephew, Otto Robert Frisch, who was also a physicist, came to join her there.
Aunt? 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 Lisa, how are you, my dear? Merry Christmas, Aunt.
I need your help. Come on, let's go out.
But I was hoping you'd help me.
Back in Berlin, Han was getting strange results. He found no evidence to suggest that bombarding the uranium nucleus with neutrons had caused it to increase in size. In fact, his experiments seemed to be contaminated with radium, a smaller atom. He desperately needed Meitner's expert analysis. From afar, she was starting to suspect that something very different was happening in their experiment.
Han and Strassman are getting some strange results with the uranium work.
Really?
A couple of months ago, Han told me that they were finding radium amongst the uranium products. We are looking for a much bigger element, and here we're finding something much smaller. I urged Han to check again. It couldn't be radium. And now he writes to me and tells me that it's not radium, it's barium.
That's even smaller.
Exactly. Han is sure that it's another error, but I don't know anymore. It is at least possible. possible that barium is being produced.
So Hans still needs you to interpret the data.
It is my work too, you know.
Exactly.
Well, I can't be there, can I? Come on, let's walk.
Surely he's made a mistake, hasn't he? He hasn't done what you told him to.
Oh, my darling Robert, he may not be a brilliant theorist, but he's too good a chemist to get this wrong.
If you imagine a drop of water, a big drop, it's unstable, on the verge of breaking apart. It turns out that a big nucleus like uranium is just like that. Now, for 4 years, Meitner and Hahn and all other physicists had thought that if you pump more neutrons into this nucleus, it'll just get bigger and heavier. But suddenly, Meitner and Frisch, out in the midday snow, realized that this nucleus might just get so big that it would split in two.
If the nucleus is so big that it has trouble staying together, then couldn't just a little tiny jog from a neutron...
Yes, but if the nucleus did split, the two halves would fly apart with a huge amount of energy. Where's that energy going to come from?
How much energy?
Well, we worked out that the mutual repulsion between two nuclei would generate about 200 million electron volts. But something has to supply that energy.
Wait, let me do a packing friction calculation. The two nuclei are lighter than the original nucleus of the uranium by about 1/5 of a proton in mass.
What? So some mass has been lost. Einstein's E equals mc squared.
If we multiply the lost mass by the speed of light squared, we get 200 million electron volts. He split the atom.
No. You've split the atom.
It was an amazing discovery. Of course, in the laboratory, we're talking about tiny amounts of uranium and correspondingly tiny amounts of energy. But the point is that the amount of energy released was relatively large, and that it came from the mass of the uranium itself. The energy released was entirely consistent with Einstein's equation, E equals mc squared.
Meitner and Frisch published the discovery of what they called nuclear fission to great acclaim. But betrayal awaited them. Otto Hahn was under pressure from the Nazi regime to write his Jewish colleague out of the story. He alone was awarded the 1944 Nobel Prize for the discovery. In his speech, he barely mentioned the leading role of Meitner. Bizarrely, even after the war, Hahn maintained it was he, and not Meitner, who had discovered nuclear fission.
Now I want to write something personal, which disturbs me and which I ask you to read with more than 40-year friendship in mind and with the desire to understand me. I am now referred to as Hahn's longtime co-worker. How would you feel if you were only characterized as the longtime co-worker of me? After the last 15 years, which I wouldn't wish on any good friend, shall my scientific past also be taken from me? Is that fair? And why is it happening?
Lisa Meitner had been working on this for 30 years. She'd only broken apart a handful of atoms, but that was enough. Once she had broken even one, the genie was out of the bottle. What Meitner had started, after that, physicists around the world began to realize they could take it a lot further.
In 1942, an intense effort to build an atom bomb was begun. All over America, secret installations sprang up under the code name the Manhattan Project.
Meitner was asked to join the Manhattan Project, and she refused. She refused to have anything to do with the atomic bomb. But Robert Frisch was different. He was an important member of the team because he was convinced of the need to beat the Nazis in a nuclear arms race.
A nuclear bomb was never used on Germany, but the atomic bombs dropped on Hiroshima and Nagasaki demonstrated the terrible destructive power of E equals mc squared. Vast amounts of energy in the form of electromagnetic radiation were released from a few pounds of uranium and plutonium. While the pure inquisitiveness of the world's most gifted scientists ironically had brought humanity a weapon of mass destruction, the equation's life has a parallel story of creation and beauty. Today, young physicists carry on Einstein's quest. Ever since its birth, E equals mc squared has been used to delve into the depths of time, to answer the biggest question of all: where did we come from? At particle accelerators, researchers propel atomic particles to the speed of light and smash them together, creating conditions like those in the Big Bang.
E equals mc squared actually tells us how the Big Bang itself happened. In the first moments of creation, the universe was this immensely dense, immensely concentrated eruption of energy. As it rushed apart and expanded, huge amounts of energy, or E, were converted into mass, or M. Pure energy became matter. It became the particles and atoms, and it eventually formed the first stars.
Our sun is a huge furnace floating in space, and it's powered by E equals mc squared. Now, it turns out every second, 4 million tons of solid mass of the sun disappears, comes out as energy, not just a little bit of energy. It's enough to light up our entire solar system, make the solar system glow with heat and light.
And not only do stars emit energy in accordance with E equals mc squared, the whole process actually creates life itself. Eventually, a massive star dies. The debris floats around, clusters together, gets pulled into the orbits of another star, and becomes a planet. We humans and the Earth we stand on are made of stardust. We are a direct product of E equals mc squared.
Building on the work of scientists through the ages, new generations are searching for answers. Using bold new tools that reach almost to the speed of light, they can now ask questions that their predecessors could never have even imagined. As Einstein himself knew, the journey of discovery is sometimes painful, sometimes joyful. It is as old as human curiosity itself, and never, ever ends.
We gave top physicists 2 short minutes to explain Einstein's big idea. On NOVA's website, you can hear how they did it, tell us what you think about this program, and much more. Find it on pbs.org. To order this program on DVD or VHS or the book E=mc², a biography of the world's most famous equation, please call WGBH Boston Video at 1-800-255-9424.